Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering. I welcome you all for this course. So, in the first module, we have designed it based on the previous topics of thermodynamics. So, in this module, we will try to review the basic concepts of thermodynamics, different terminologies that are used in this basic course on thermodynamics. Then we will touch upon another fundamental topics of interest, which is the pure substance, properties of pure substance. So, there we will touch upon on a major aspects about the different equations that are used for perfect gas. Side by side, we will also have emphasis on mainly water and saturated water, superheated water and superheated steam and their properties. So, in this first module, we will try to touch upon how to use steam tables, property data tables that are very vital for subsequent lectures in this course. And in these subsequent lectures, we have mainly dealing with steam power systems, gas power systems and renewable energy power systems. So, all these things are like power generating devices, but very basic concepts for these power generating devices comes from the theory or laws of thermodynamics, that is first law and second law. So, these two things subsequently lead to the concept of heat engines, in which it is possible for any device that works in a cyclic manner, which can produce low grade energy of heat to the shaft work or work output. So, with this concept all subsequent modules are designed. So, at this point I need to emphasize that basic aspects of thermodynamics is very vital, and so however, we will restrict our attention to particularly to some concepts which we will be using frequently in the subsequent module. So, let us revisit the basic aspects of thermodynamics. So, in this first lecture, which is part 1, we will talk about thermodynamic concepts. So, mainly we will be discussing on terminologies, then first law of thermodynamics, steady flow energy equations. Then we have property relationship, and mainly we will see what is perfect gas and what is imperfect gas. Then we will touch upon some of the steady flow devices, which are basically governed by the first law or steady flow energy equations. So, to start with the terminology, let us try to understand that in our basic introduction course I have emphasized these figures. So, basically there are three types of energy: thermal energy, electrical energy and mechanical energy, and these energies are very vital for the human necessity or human mankind survival. So, however, the conversion of one form of energy to other form is possible. So, it is very easy that we can have conversion between mechanical and electrical. Then we can also have mechanical and thermal, again from thermal and electrical. But however, apart from these basic energy sources, and for them the main basic resources is the fossil fuel. But however, there are other types of energy which are available in the nature, like solar, geothermal, chemical fuels, nuclear, hydro or wind. that are also available. So, those are the kind of what we call them as a renewable form of energy or alternative resources, but they can be coupled either to any one of the energy resources, and ultimately we need to have electrical energy in the end for our survival of the mankind. And in order to have this particular conversion, we require the concept of thermodynamics. So, ideally speaking, that the word thermodynamics is derived from a Greek word, that is thermi and dynamics. Thermi means it is heat, dynamics means power. So, conversion of heat to power is the basic necessity to deal with various application areas. And in these various application areas, we have power plants which is either steam or gas based, or we can have IC engines, we can have gas turbine engines or aircraft engines. Then we will also have refrigeration and air conditioning. However, in this power plant system engineering, we will be talking about mainly the production, those devices that can produce power. So, refrigeration and air conditioning is a separate topics, because it consumes power for cooling purposes. So, that is a different topics of interest, but however, our main attention will touch upon the production of power through various means, which I have mentioned in this figure. Then moving further, to deal with different terminology, we all know that in thermodynamics we define a systems in which our attention is focused, and any systems is associated with its boundary. That means, any change in the systems is felt within this boundary, and beyond this boundary we call this as a surroundings. So, system and surroundings constitutes universe. So, this is the very basic philosophy of thermodynamics, and of course, one can think of this boundary as a fixed boundary or a moving boundary. Then while talking about the systems, the system with thermodynamic viewpoint, system is treated as a closed systems or open systems. So, in a closed systems, we can say that there are some fixed amount of mass which is concentrated in these systems, and this mass can be compressed or expanded within its own systems. That means, change of state of the system of the mass is allowed within that vicinity, but however, the system is not allowed to have interaction of mass from the outside. So, that is what we say for a closed systems, there is no mass interactions, but it has a flexibility. The closed system has a flexibility, it can interact with surroundings by virtue of energy interactions. Now, when you move on to an open systems, and many times we refer it as a control volume, so in which that the volume of the system is going to change, because this open system allows for the mass to come in and to come out, and of course, it also allows energy to enter into this system and it can go out. So, through this process, the open systems allows both mass and energy interactions. And on a special case, when we have this there is no mass and energy interactions is possible, so we call it as a isolated system. Then moving further, we in thermodynamics we defined a state. State is a means is, that means, when a particular system is specified by its location or identity, and this identity is normally referred in terms of pressure volume coordinates, and we call this as a thermodynamic states. So, state means, that means, when the all properties of a system has a definite value, then it is called as a states, and properties are nothing but the coordinates of the state. Now, when the coordinates change, so that means there is a change of state. So, when there is a change of state, then it has to go in a certain path or some that means, there is a succession of change of states happens for the systems, and that we call it as a path. Now, if you identically or completely define this path, then we call this as a process. So, thermodynamically we have many processes like isothermal, isobaric, isochoric, and so many processes are there. So, that means, the mathematically we can specify how the change of state happens during this when the system goes from one point to other point. Now, when we have many number of processes, multiple number of processes, but and that happens in such a way that for a given system, when it starts with a particular location and it undergoes different states, and then obviously when it undergoes different states, it passes that means its path is specified, that means it has there is change of state. So, it is defined by some certain processes, but when you say it is a cycle, the initial state and the final state must be identical. So, what we can say define the cycle, it is as a series of change of state in which the final state is identical with the initial state, we call this as a cycle. So, in this particular figure we can say that we start with we define a state of a system at point 1 and it goes to point 2 in a path which is B, but however, again that point 2 comes back to original state in another process or path, but but what we say is that, so 1, B, 2, A and 1 forms a cycle. Then another kind of study that we also deal with or we come across is a quasi static processes. So, obviously, when there is a coordinates of a system change, we say that is a some change of state happens. So, it happens in a particular process, but what happens if this change of state happens in a very slow manner, then we view these systems as a series of changes that happens within the systems, and this change happens in a very slow manner. So, as a result, although there is a change internally, but external effect due to this change is very much negligible, because system is always said to be in equilibrium with its surroundings at all points. So, such a process we define it as a quasi static process. So, a quasi static process occurs through series of equilibrium states, and although there is a change of state, but the surroundings is not affected by this change, because system and surroundings are always in the equilibrium state. So, through a simple figure that we can explain about a quasi static process is that, if you look at this figure, we have a piston cylinder device, and in this piston we are there is a gas which is at initial state P1, B1, T1, and this initial state is happened due to a weight which is kept on these pistons. And so, we have this systems, its boundary. So, what happens, there are two instances if you remove this particular weight completely. So, obviously, the system which is at initial state will move on to this final state P2, V2, T2. So, initial coordinates of the system was P1, V1, T1, and final coordinate of the system becomes P2, V2, T2. But through this process what happens, there is a change happens, but that change was instantaneous because we have taken out this weight instantly from these pistons. But that means the point 1 goes to point 2, and the change that happens in the intermediate locations, it is a very instantaneous. So, such process cannot be called as a quasi static process. Rather, what we can think of, that this particular weight can be imagined to be have a multiple, you can divide it at a small weights that constitutes this W. That means, they have n number of weights, and this n number of weights masses are combinedly gives the total weight W. So, what we do is that you take one by one. So, when you start with initial state 1, when you take one of the weight, then it goes to another point. When you take another weight, it goes to another point, and likewise there is a change that happens, and through this process final state becomes 2. That means, when you take the last mass, then it becomes 2. So, through this process what happens, there are changes happening through these intermediate states points, but they are occurring in a very slow manner. So, we call them as equilibrium states, and complete process we call this as a quasi static process. So, this is what very vital, because most of the processes are defined in thermodynamically to happen in a quasi static manner. Then we have a concept of work and heat, because when you deal with energy, there are two variants of energy that thermodynamics tells us. One is in the form of work, other is in the form of heat. So, when we view this as a work, because either we can, work is a kind of a energy which is viewed in rising mass, or that means through that energy we can imagine that a mass can be taken from one height to other, and sometimes we call this as a PDV work, and that PDV work we normally refer it in a closed systems. Now, anything that happens by virtue of temperature difference, so those form of energy interactions we call it as a heat, and this energy interactions is possible when they cross the system boundary. That means, as long as they are within the system, we do not see it as a interactions, rather we say there is a change, but that change remains within the boundaries. When the, so that means whether you say work or heat, it is a boundary phenomena, and we view them only when they cross the boundary. Again, another important point is that the work and heat during a quasi static process depends on the path they follow. For example, in this process, if you say that the change of state that happens from 1 to 2 in a quasi static or equilibrium states manner, we can say that there is a path followed by this, and this path can be completely specified, and through this process there is an interactions either heat or work, and we call it as, so hence both heat and work are called as path functions. And of course, they are treated as a inexact or imperfect differential, and they are not associated with a particular state, rather they are associated with a process. That means, their identity is with respect to a process, not a particular state. Another point I need to emphasize here, that terminology that we used for work and heat interactions. So, these there are possibilities that heat can be added to the systems or heat can be rejected from the systems. So, when we add this heat, then Q is treated as a positive. When you take out this heat, we call this as a negative, and in same terminology, when work is done by the systems, we say it is a positive, and work is done on the systems, it is a negative. So, all these notations has to do side by side. So, heat addition means positive, work done by the system means it is positive. So, with these notations, all other consequences can be framed. Then we will move on to properties, and thermodynamically we view the properties either intensive or extensive. So, that means, every system is defined by its own identity or states. So, that state is defined by its property, pressure, volume, temperature, all are thermodynamic properties, but they are broadly categorized, either they are intensive or extensive. So, intensive properties are independent of mass and size. So, for example, temperature, pressure, density, they are treated as intensive properties. Then we have extensive properties that depends on the size of the systems, that is mass dependent. So, for example, mass, volume and energy, they are treated as a mass dependence. For example, if you can say that which property is an intensive and extensive, let us take a container or rigid systems in which has a volume V, temperature T, pressure P, mass m, and density contains a gas which has a density rho. Now, what we do? We make a partition. We can make a partition, that means, this is your initial state and we make this partition state. When you make a partition, what may happen? Mass may be half. So, that means, you can, if you could just drop a partition among them, mass we can make it half, volume also you can make it half, but both partitions, the gas or fluid which is in the both the partitions, they will have a same pressure, same temperature and same density. That means, pressure, temperature and density do not change, whether mass changes. So, that means pressure, temperature, density, they are mass independent. That is what we call this name as a intensive properties, and others are extensive properties. Now, coming back to energy, energy is nothing but the potential of flow that exists in various form, chemical, mechanical, and mechanical also you can have a kinetic and potential. Then you can also have thermal, nuclear, and apart from that we will also deal with the another kind of energy, that is called the internal energy, which happens within the systems, and it is a microscopic form of energy. And that, why did you define this? Because it talks about the molecular motions which happens in the either there can be translation, vibration or rotations, and combinedly we call this as a internal energy. And when we say that internal energy is associated with the kinetic energy of the molecules, we say it is a sensible energy, and that is happens due to change in the temperatures. So, when this internal energy is used for binding the molecules in its phase, then and we want to go for a change of phase, then such energy we call as a latent energy. But however, this internal energy is a strong function of temperatures, and that is for pure substance. And in our entire course we will talk about internal energy, the function of internal energy as a temperature only. Then let us review the first law of thermodynamics. So, it says that energy can be, it is a what we call as a conservation of energy principles. So, it says that energy of the system undergoing a change or processes can be increased or decreased by exchange with the surroundings, and they can be converted from one form to other within that systems. So, through this process it says that energy is conserved. There is a possibility of change of energy from in one form to other form, but the accountability is that how total energy which enters into the systems, and that must go out of the systems. So, energy auditing will tell you that total accounting of energy that enters and goes, they must balance each other. But however, the conversion is allowed, but it does not indicate whether the conversion of energy from one takes place from one form to other completely or performed perfectly or not. And to define this energy or to define the first law, a most ideal system that we can choose is open system, because an open systems allows both mass and energy interactions, and this energy interaction is possible either by heat or work. So, hence we will view this open system as a benchmark to define this first law. Now, apart from this, we also introduce one other form of energy which is called as a flow energy, and the flow energy that comes because there is a mass that enters into it. So, we say that mass has certain energy which pushes the fluid into the systems, and that fluid also gets pushed out from the systems, and this change happens by virtue of this pressure difference, and we combinedly call them as a flow energy. So, the total energy that enters, either it can enter as a potential energy form, kinetic energy form, internal energy form or flow energy form, and also this energy that can leave out from the system is also in the same form. Apart from that, the open system also interacts with heat or work. Now, a most ideal way of looking at this change of state is to happen is that it is a completely transient state, where mass inflow, mass outflow can also vary with time, but ideally for to frame our first law in a very precise manner, we will assume it to be a steady state, steady flow systems, SSF system, and for that we are going to see that how we need to make this energy auditing which takes care about the all form of energy. So, a steady flow systems allows the heat interactions, work interactions apart from this mechanical energy. That mechanical energy comes by virtue of potential and kinetic energies. Now, let us see that do this energy auditing for these open systems. So, in this figure if you apply this first law, what we can see, what is entering into the systems, that is state 1 and delta Q, that is through heat interactions. So, this delta Q is nothing but the heat, net heat which is gets added into system. So, that is what it is taken as a positives. So, that is entire thing that enters is taken as a positive, and the net work interactions, that is work done by the systems, we interpret as a delta W, or we sometimes we call as a steady flow work, and this is what it is in the right hand side of these equations. Apart from that, what is entering through this state 1 is combination of PE1, KE1, IE1 and FE1. Similarly, what goes out is PE2, KE2, IE2 and FE2. So, these are the things that goes out. Now, individually we can interpret what is potential energy mg times z, kinetic energy half mvs square, and internal energy static mass times its small u is internal energy, and flow work is interpreted as pressure times its specific volume or volume. So, it is PV1. So, likewise we can interpret. So, heat transfer that crosses the boundary, it is net heat added delta Q, steady flow heat transfer delta W. Now, here we can say this is a path functions. So, we have to define and we view them when they cross the systems, and as I mentioned that when you say it is a delta Q, it occurs by virtue of temperature difference, and when you say steady flow work transfer for an open systems, it is interpreted in the integral of VdP. Now, to define these things, we have two things here. One is we have to define the path, because both heat and work are path functions. So, for that reasons, a general relationship for pressure volume we can write as a PV to the power n is equal to constants. And this n is going to vary whether it is a constant pressure, constant volume, isothermal, isentropic or polytropic processes. And here also we will define another term, that is Cn, and that Cn stands as a specific heat, and also it depends for what type of process it is. So, whether it is a constant pressure Cp or it is a constant volume, it is Cv, isothermal process it is infinity, and isentropic process 0, and polytropic process is defined in this manner. So, through this process, through this exponential term n, we can define the various terms in these equations. And many times we also interpret the steady flow energy equations per unit mass basis. So, we can have a specific volume, you can define the specific volume as total V by m, or specific internal energy U by m. So, accordingly per unit mass basis, if it is a fixed mass entering and leaving the open systems, we can simplify these equations. And in fact, this particular figure also shows for a different value of n, what are the PdV work that can be defined. Another term for the open systems that or the first law talks about, apart from the internal energy, we define the term enthalpy. So, enthalpy is nothing but this is a like internal energy plus flow energy. So, H is equal to U plus PV, and there is also a definition for specific heats, which is a function of internal energy as a change in the internal energy with respect to temperatures. So, there are for gases we can have two specific heats, because we can view this specific heat in a two different way, either at constant volume or at constant pressures. So, accordingly with specific heats we define it as a constant pressure or constant volume. Difference between them is the characteristics gas constant for a given fluid. Then we also have specific heat ratio K, that is Cp by Cv, and many times we also interpret that if Cv is a function of temperatures. So, accordingly it cannot be taken as a constant, so it has to be in the integral form. Similarly, for enthalpy as well, in which Cp can be treated as a function of temperatures. So, this is the summary of open systems. Now, moving to the closed systems. In the closed systems, we mentioned that this closed system only energy interaction, there is no mass interactions. So, in that way, if you start our basic equations, that is first law for an open systems, and try to apply it for a closed systems, many terms will get cancelled That means, we do not have these terms because this changes, the first law does not allow them, and this also there is flow energy term will also vanish. So, first law that becomes that u 1 plus delta q is equal to u 2 plus delta w, and ultimately we say delta q is equal to delta u plus delta w, and in a very differential form we say dou q is equal to du plus dw. So, here these are, since it is a path function, it is inexact differential, when since it is u is a property, so it is an exact differential. So, this is nothing but the first law for the closed systems. Now, already I defined cycle. So, cycle means, in our subsequent lecture we will talk about that if you want to extract energy, convert energy from one form to other, particularly heat to work, you need a working fluid that has to operate in a cyclic manner, and that working fluid has to undergo some change of states, and this change of states is accounted such that it forms a cycles. For example, this is a particular cycle and it is nothing but a diesel cycle. The process goes from 1, 2, 3, 4 in a particular fashion, and in a similarly same process can be done in a TS diagrams. So, through this concept we can say that if you want to extract heat from a fuel, then we must use a working fluid that works in a continuous manner such that this working fluid changes its state from 1 to 2 to 3, then 4, then 1, and so that it forms a cycle. And for this particular diesel cycle, which is seen that since initial states and final states are identical, there is no change in the internal energy, but this dq delta q can be equal to delta w, and this can be viewed it as a closed systems. So, it says that the energy auditing will tell that total change in the heat interactions also balances to work. So, delta q is equal to delta w. So, this is how the first law for a cycle. Now, previously we might have in the previous courses of thermodynamics, we might have known different processes. We are not going deep into all those things. Rather, I will try to emphasize what are the different thermodynamic, and this particular table talks about the summary sheet for different processes: isothermal, constant pressure, constant volume, reversible adiabatic, polytropic, throttling, which are commonly used in all kinds of thermodynamic devices, and correspondingly their state relationship, that means how these pressure volume relations are taken into account, and other properties like we look at the change of state in terms of internal energy, enthalpy, entropy, non-flow work, flow work, heat transfers. So, this is the summary sheet which is there, and the derivations are already there in the basic level of thermodynamics course, which we are not going into deep into this. Now, another point that I need to emphasize here, many times we will be talking about perfect gas and non-perfect gas. So, basically we all know the equation for an ideal gas, that is P V is equal to R T or MRT. Now, what happens when we have this ideal gas equation which says that pressure volume characteristics is equal to M P capital B is equal to M R T, where its P stands for pressure, V stands for total volume, M stands for mass, R stands for characteristics gas constant for that gas, and T stands for the absolute temperature. So, this equation holds good for an ideal gas. Now, if it is a non-ideal gas, then this equations is changes to in this form, where you introduce a term what is called as Z, which is called as a compressibility factor. That means identically, that means we do not if it is a non-perfect gas, we say that why you say it is not an ideal gas, because the molecules are close enough to exert forces on each other. So, that when the perfect gas is highly compressed and highly cooled and in a critical conditions. So, it means that there is a intermolecular force that binds the molecules, that is one part. Second option is second thing that ideal gas law is not violated because each molecules is tried to occupy some space. So, the total volume we accounted as V is less than that. So, for that reasons we have different equation of states, that is called as van der Waals equation state. There are many such thermodynamic states for non ideal gases can be specified, but however, we will not deal into this, but what I am trying to say here is that if there is a non ideal non perfect gas, how do you deal with? So, we introduce a factor, that same equation we introduce a term what is called as a compressibility factor, and this compressibility factor is plotted in a chart, and this chart has y axis as a z and x axis is reduced pressure, and there are plots like different values of reduced temperatures. So, we say reduced pressure and reduced temperature, they are defined by P by P c, and that is P r is equal to P by P c and T r is equal to T by T c, and P and T are the pressure or any arbitrary pressure and temperatures that the gas is specified. But P c and T c, they are called as critical values of pressure, that means pressure and temperature at critical conditions. So, it varies from different gas to gas. So, for these values we can refer gas tables, like nitrogen will have a different values of P c and T c, oxygen will have different values of P c and T c. So, those numbers you can find out from the tables which are available in any common textbooks. This is, that means when you know P c and T c, then we can define this P r. So, what is the significance of these two? So, that means if you know this P r and T r for a given gas, then we can easily use this chart to find out the deviation or compressibility factor, and when you find this compressibility factor, then you can see that whether the assumption of ideal gas equations is violated or not. So, that is the advantage of introducing this compressibility chart, but however, more or less unless and until we require very accurate informations, in most of the cases validity of ideal gas is unanimously accepted. And the last segment of this is to introduce some steady flow devices which is governed by from this first law of thermodynamics, and a steady flow devices are nothing but that means they operate on steady processes, thermodynamic processes, and in which the fluid flows through the control volume steadily. What we view is that fluid properties can change from point to point, and at a fixed point they remain same. At fixed point they remains same for the entire processes. And in this steady flow device category, we have like nozzles and diffuser, turbines and compressors, heat exchanger, throttle valves. So, what does this nozzle do? Nozzle expands the fluid at the expense, that means velocity increases at the expense of pressure, and diffuser does exactly opposite version of nozzles. Then we have turbines and compressors. In the turbines the gas expands, and in the compressor gas is compressed. So, this is what we say turbines, and this is what the compressors. So, for compressor we require work input, but turbine produces the power. Then we have heat exchanger. Heat exchanger means it does not have a role of any producing the power, it is mainly dealt with the interaction of heat. So, we can have two ways, that means when you say it is a control volume, two fluids can mix each other. So, you can have a mixing chamber. So, that means the and combined fluid can leave. So, that is one way. Other way is that we can pass the two fluids in two different entities and they do not mix each other, rather they only exchange the heat. So, that way we call this as a heat exchanger. Then another kind of device which is a throttle valve. So, throttle valve is a kind of a plug or capillary tube. What it does there is a drop in pressures. So, through these throttling valve devices, what remains constant is the enthalpy. So, if you look at enthalpy is equal to H is equal to U plus PV. So, in a throttle valve enthalpy remains constant. So, however, your initial state, your temperature T1 may be equal to T2, enthalpy may be same, but then the change in the volume, increase in the pressure and volume will match such that enthalpy remains constant. And looking at those simple relations, the steady flow energy equations can be framed for steam generator or heat exchanger, steam turbines, compressors, the nozzles and diffuser we can frame. So, all these derivations are available in these books. So, this is nothing new, but this can be derived based on this figure in these equations. So, we start with these equations, that is first law equation for a steady flow energy systems. Based on the nature of the device, many terms can be neglected for a particular steady flow device, and accordingly we can frame these steady flow energy equations for different components like generator, steam generator, heat exchanger and gas and steam turbines, compressors, nozzles and diffuser, because each devices has a specific role to perform. So, this is all about for the discussion. So, with our discussion, let me try to solve some numerical problems which we have covered in this lecture. So, in this first problem I have just given a demonstration that whether we have the ideal gas equation which you all know, at the same time if the gas is treated as a non-ideal or non-perfect gas, or you do not use this non-perfect gas, then what is the solution? So, for that this particular problem demonstrates that we have a tank, rigid tank that stores nitrogen, and it has a volume as 0.3 meter cube, and it has a pressure P 70 bar, T is equal to 23 degree centigrade or 296 Kelvin. So, this is the gas which is stored in the things, and we need to find out mass by two means. One, by assuming a non-perfect gas, and second, if the perfect gas equation is assumed. So, in other words we say, let us say nitrogen is a non-perfect gas, then how do you calculate the mass? So, for that what you have to refer? You have to refer the data table which is in the any thermodynamics books, and that data table for gases or for pure gases. So, for nitrogen, this will implies two important value for what is called as critical values. And that is one number is critical pressure. This number we can note it down as 34 bar. Temperature, for the critical temperature for nitrogen is 126.2 Kelvin, and more details about these critical conditions will come in the next class, in which we will deal with the pure substance. So, for the time being, let us see this is the critical pressure and critical temperature. Then we can find the reduced pressure and temperature. So, they are P r, that is equal to P by P c. So, this number is 70 by 34 and that number is 2.05, and again T r, that is T by T c, this number is 296 divided by 126.2, it is 2.34. So, we have two numbers P r and T r. Now, refer the generalized compressibility chart. In fact, this chart is available in any of these thermodynamics books. This particular chart was taken from this book, that is Moran and Shapiro. The snapshot of this graph shows this way. So, what we say is that for this P r and T r, so we have P r is close to 2. So, this x axis talks about P r, that is 2, and these are the lines of constant TR. So, constant TR lines starts somewhere in this line, and it is very close to this particular one. So, if you go along this vertical, the TR line will stop somewhere here, and this particular, if you drop horizontal line onto this, then we can drop down close to the value of Z, which is approximately 0.98, or it is, we can say it is close to 1. So, putting this, we can write this main equations for non-perfect gas. We say P B is equal to m into Z R T. So, from these equations we can say Z is 0.98, and we can say what is mass is equal to P B by Z R T, and for nitrogens we can take this R as, note down this R as 0.297 kilojoule per kg Kelvin. So, m becomes 70 into 10 to the power 5, B 0.3 divided by 0.98 into 297 into 296. So, this will give you m is equal to 24.375 kg. Now, if you say it is a perfect gas, other equation will turn out to be P V is equal to m R T, and through this process we can also calculate mass for an ideal gas. So, we say if nitrogen treated as an ideal gas, m ideal is equal to P V by R T, and this number happens to be 23.88 kg. So, the questions was asked what is the percentage of error introduced. So, percentage of error for this mass calculation would be m actual mass, m ideal gas mass divided by m ideal. So, how it deviates from this into 100%, that is in the percentage. So, this happens to be 24.375 minus 23.88 divided by 23.88. So, it is approximately 0.2 or 0.02 or close to 2%. So, for this problem, if you say that nitrogen is treated as a non-ideal gas, then we will introduce only 2% error. So, the another problem that is based on the steady flow devices. In this case, it is a water heater and it operates in a steady flow conditions. It takes water at certain enthalpies and temperatures, and water is also heated with a steam, and the steam is supplied at certain conditions 105 degree centigrade and 2680 enthalpy, and of course, the mixture is living at 100 degree centigrade and 420 kilojoule per kg. We need to find the supply rate of the steam. So, to do that you can recall simply a open systems that consists one fluid in and there is another fluid that enters and there, but one fluid leaves, single fluid leaves. So, that is two inlet and one outlet. So, one case we say it is a water, other case we say steam. So, it is a water heater. So, conditions of water, that means we say mass of water. Here also we have enthalpy of water, then mass of steam, enthalpy of steam, and we have mixture, that is mm and hm. So, there are two equations that we can frame for this water heater problem. One is mass balance, we say that MW plus MS is equal to MM. Then we have energy balance. By neglecting all other terms and only retaining the heat terms, we write like we say delta W to be 0, delta Q to be 0, delta change in the potential energy is 0, change in the kinetic energy is 0. So, we can write steady state, steady flow equation as MW HW plus MS HS is equal to MM HM. Now, introduce MM in these equations. So, it can be simplified as MW HW plus MS HS is equal to MW plus MS into HM. Now, what we require is the supply rate of steam. So, we require HS. So, accordingly we can write as supply rate of steam means MS, we require MS. So, we have to express in terms of MS, that is equal to MW into HM minus HW divided by HS minus HM. So, data that is given here is MW 4.2 kg per second. Then we have HW water 315 kilojoule per kg, HS 2680 kilojoule per kg, then HM mixture is 420 kilojoule per kg. Now, inserting this value, we write MS is equal to 4.2 into 420 minus 315 divided by 2680 minus 420. So, we say MS is equal to 0.195 kg per second, or approximately in terms of, since this number is low, we can convert it into kg per hour. So, it is 703 kg per hour. Just multiply 3600 to this MS value, we have this. So, supply rate of steam is 703 kg per hour. So, these are the two sample problems for this our lecture today. With this, I conclude this lecture. Thank you for your attention.